start? Shall I start?
Wait a second. Yeah, you can start.
A second quantization. So, given so first fact, in first quantization scheme, the probability of existence, the probability of particle existence somewhere in the whole space as in case of electron is set to 1. That this implies for existence, for example, Schrödinger equation. Minus h squared over 2m plus cx plus vx cx is equal. Okay. In second quantization, second fact, in second quantization, the probability of existence of electron somewhere in the whole space is not necessarily 1, and there can be probability of existence more than 1 interacting particles as electrons or whole with phonon, etc. Right? So, yeah, Wojtek, is it clear what I have said?
Yep.
Wojtek. Philip, is it clear what I said? Is it clear?
Yeah.
Yes, it is.
Okay. Okay, so give me a second.
The topic of normalization of this many particle wave functions is interesting.
Yes, of course it is, but we can always limit ourselves to certain system. Okay. So what is next? So let's say, so let me start from in second quantization. Wave function scalar value function is replaced with wave function operator. So maybe it is okay. This is third fact. Third fact. So, and then we have assignments. So we have, in a sense,
We have to move the paper a little bit.
yeah.
Oh, yeah.
So do you understand this operation that I have written? Do you have any suggestion or comments? Please analyze it. Do you have any comment?
This C is the annihilation operator, or what is it?
Correct. Correct.
Okay.
And what else? What else?
Okay. This I don't know what is the name of it. Phi, Phi, I think. It is some It is some function of
It is what? It's what? Sorry.
it's just the scalar function. Oh no, it's not a scalar function because no, it is. It is a scalar function of the place that
What is the summation? What is the summation? What is the summation about? What does it come from? Summation. Summation is from what? Why we have a summation here? Why? What's the response? Why we have summation?
because we want to use this annihilation operator in a space. So not in one point, but in some defined space. I don't know.
Because we are trying to find out how many particles are in each state.
Say again, Wojtek. Wojtek, say again. What did you say?
We are trying to find out how many particles are in each state. We're not interested in state of only one particle. We are interested in many body systems. So we are interested in the state of a whole system.
What this is I index about? What this is I index? What does it mean? I index here.
Is some index, we are indexing the particles, right?
What's the hypothesis? Okay, so I will ask. Is it? Yeah. So who can answer this question? Can you answer, Philip? What this is I about? Index. What this index refers to?
Borges said that it is about enumerating the particles. And I think that it can be
How
true.
about energy? Maybe it is about energy. Is it about energy or not?
I don't think so, but I'm not sure.
Wojtek, what this is about?
I don't know.
Try to guess. Don't say
No.
no, just try to guess.
Sorry, I cannot know.
Okay, and okay, so okay, so we are still thinking. Okay, so let us imagine there is no such sum. So I would hypothesize that this is about energy or position. What do you think? I would hypothesize this is about that I is here energy actually.
I think that I will be about energy because the scalar function between the sum and any annihilation operator depends uh, on the position.
Look, this is like annihilation with the given energy. So we run. So here we're supposed to have actually integral or sum. Do you understand what I'm saying?
Yeah.
It's very well done in Fetter-Walecka book. In Fetter-Walecka, okay, but before moving on, so what are the relation commutation annihilation relations? What they are about? Because we have two types of yeah, we have fermions and bosons. Is
Yeah.
there any relation that describes them very well? So the commutation and anti-commutation for bosons or fermions. Wojtek, did you have a quantum mechanics or not yet?
Yeah, I had it.
You have it right now, or you will have it?
I had it on the last
You
semester
I see. With who?
with Professor Tosiek.
Oh, I see. Okay, so you had first quantization for sure, right?
Yep.
Okay, so what are these operators about?
So you're asking about that they're independent and in time and they're
Yeah, but I'm
described.
asking about Fermi statistics and boson statistics. What's the difference?
Oh, I don't know.
What's the difference? Fermions. You don't know what is a fermion? What is a fermion? Fermion.
So
How would you define?
fermions are like we have bosons, so the other type of particles are
Okay, so
fermions.
what are bosons then? Okay, bosons or fermions. Tell me about one of them.
I can say.
So fermions are particles that contains there were leptons, like electrons, and the baryons, so the proton, neutron. The
Yeah.
boson is the, for example, photon, the Higgs boson, the gluon. So the bosons describes interactions, and the fermions are the basic elements that create the matter.
Okay, but yeah, so I want to yeah, so in a sense, but can I squeeze fermions infinitely much or not?
So fermions are, but it depends. The leptons are the smallest parts, but the baryons are created out of quarks.
Okay, I have two electrons. Can I squeeze them infinitely? Electrons are what type of particles? Fermions or bosons?
Are fermions.
Yes. Can I squeeze two electrons? Can I bring them together?
I don't think so.
Of course. And so so fermions cannot be squeezed infinitely
Yep.
much, but photons. I have photons. Can I squeeze photons to one place?
Yeah,
And photons are what type of particles?
are bosons.
Boson. There is a boson statistics that you can squeeze. You can have infinite density. Phonons are bosons. Fermions. Phonons are bosons. Then photons are bosons. Cooper-Parr are quasi-bosons. So you have bosons, right? And then you have fermions. And what's special? If I exchange position of two bosons and spin, I take two bosons, I exchange their position. The wave function will remain the same or will change?
Of two bosons.
Yeah.
I don't think so, because the Pauli principle is correct for fermions.
Yeah, if we
Yeah.
switch,
Yeah.
if we switch in a multi particle wave function to bosons or boson and fermion, nothing happens. It only happens it change the sign, sign, not the function, not the sinus, but we get minus if we switch to fermions.
Okay, so exchange of both. There's connection between spin and statistics, and it tells you that exchange of two bosons in position and spin will do nothing. So wave function is symmetric against change, and exchange of position and momentum of fermions will bring minus to the function. So function is antisymmetric, which means that two fermions cannot be at the same time because then the wave function becomes zero simply. So it's improbable, right? Is it
Yeah.
Is it understandable what I'm saying?
Yeah.
Yes.
Okay. So we need to incorporate, but before moving on, what's the prototype of creation and annihilation operators in first quantization? Because we talked about what's the main philosophy of creation and annihilation operators.
Yeah, if we have a Fock representation of a multi-particle, I don't know. Okay, if we have a wave function of many particles, the annihilation operator that's connected with some particle, with some momentum, with some spin, and with some type, so fermion or boson, we annihilate. So we break, this state in this multi-particle wave function, it disappear. And if we have conjugate operator, so creation operator, it adds this state in the first position in this multi-particle wave function.
I think you start to go. By the way, Arthur is with us, or he has disappeared once forever.
Yes, I'm back.
Okay, Arthur, tell us, what is the example of appearance of creator and annihilator operator? Have you ever met in quantum mechanics, creator and annihilator operator?
I can't remember, not recently.
Okay. Wojtek, what is the simplest case of occurrence of creator and annihilator operator?
Maybe.
Oh, the harmonic oscillator.
Yes.
Oh yeah.
And in harmonic oscillator, what is special about creator and annihilator operator? What is special? Wojtek, what's the special in harmonic oscillator? Arthur, have you met harmonic oscillator in quantum mechanics?
Yes, I've met.
Do you remember how to define a Hamiltonian by creation and annihilation operator?
Of those two operators, I don't remember.
Wojtek.
So it was multiplying the bra times cat times bra. Am I remembering that right? So the creation times annihilation, something like that.
Well, there was some correlation with number of particles. What was the number of particles? Number of particles and harmonic oscillator. That's very important, Wojtek. I'm waiting for your answer.
Yeah,
So there was,
I know.
okay, what is special about energy spectrum of harmonic oscillator? What is the difference between energy levels? Different energy levels are what? It's very
Different. The different.
Yeah, but the distance between the energy levels is what in harmonic oscillator?
Is equal.
Oh, yeah. So it allows for what? What does it allow for? There's equal distance. How we can write operator? How we can write operator then?
We can like a h bar times the times omega.
Okay.
And then
okay, this will be fact free. Okay, h bar omega, and then what?
We are multiplying it by n and a half, n plus a half.
This one.
Or
yeah. So this is
and
Hamiltonian.
Yes,
Hamiltonian. Or
I have
you don't see?
I have a question. This n with this, I don't know, hat is just number of particles times
Yes.
the square of the amplitudes of the wave function. I think
So this is okay.
That.
By the way, first thing is just here. I is energy index. Just to finish this one. So this is third fact is here, right?
this is energy index. And this is second. And then, so just before it. So here we cite and CI is annihilation operator for I've energy state, right? So writing in such a way allows you to write different. So this is for creation operator for one particle only, right? Energy state of one particle. So this annihilates one particle with. So in a sense, particle can have different energies, and I level can be annihilated, right? So removed. So since you have many energy levels in, you can associate for you. So this is act of removing of one energy level. Wojtek, do you understand what I'm saying?
Yeah.
Right? So this is like different meaning to wave function is assigned, right? And also, it also works in that its conjugate is of course some or this. So Professor Rębieliński from Łódź University of Łódź like to make such, sigma with integral together, right? You understand the meaning, right? So it was conjugated wave function, right? And it was actually creation operator. So this is very, very important to. So this is like different ontology for wave function, for field operators annihilation and for field operator creation. Do you understand what this is about, right? CI
Yes.
is I've energy creator operator, and CI is wave function conjugate from first quantization, right? Right? You understand? First quantization, right?
Yes.
Okay, so in a sense, we do such act that we multiply wave function by creation or annihilation operator, and we sum over. That is it. Okay, so we multiply K energy wave function by corresponding creation or annihilation operator, and we sum over the whole space, right? So in that way, we get object known as the operator of for in those two objects we get it, right? Field, right? So and then okay, so this is first fact. Fourth fact is particle operator is like okay, so this is A. So this is for particle number operator, right? You agree?
Yes.
And can you give me a formula, Wojtek? What is A and A dagger? You're supposed to know this formula pretty much. How does it refer to momentum?
Momentum.
Those, yeah. How does it refer? Or maybe Philip will know.
No, I only know how does it
so
affect
you are
wave function.
you're thinking about how the momentum is the equation for momentum that contains A?
I want to know how to you are given standard Hamiltonian of harmonic oscillator. How to relate wave function, how to create
But so by a momentum and placement?
momentum and position, right?
Oh, yes. So the A dash will be equal to the square root of mass times angular, omega over 2h bar. And it's multiplied by a sum of position and momentum multiplied by imaginary number over mass times momentum.
Is it fine right now?
Mass times omega.
Now it's okay?
Yeah, and yeah, right now it's okay.
And then it's conjugated, right?
Yep.
Arthur, do you understand what this is about?
Yes,
We
I understand it.
We make it as linear combination of two conjugate variables. And it simply becomes very, how to say, it's very compact. Right. So, right. So in a sense, okay. So we know already something, and then, okay. So this is third fact, fourth fact. Okay. All right. So, okay. So doing so. So the prototype of this creation and annihilation operator is, is like that. Okay, now what is the construction of Hamiltonian? Maybe I will use the same part because it's okay. So Hamiltonian in second quantization, how I can use it?
Oh, you have some problem with camera.
No, I don't. Actually, I move it on purpose. Okay, so please tell me
No,
now.
but it
vibrates or what?
No, I can't remember. I can describe it. There are plenty of some kind of errors.
It is like that. And now I epsilon, okay. Oh, that's really strange. Maybe okay. There is no camera. I don't know. Okay. Okay, and okay. So do you see now?
Yes.
Yeah, but the quality is poor.
Unfortunately, it is as it is. So, okay. Second quantization. Okay, so actually, in most general case, we have there must be a lot of philosophy part, unfortunately, today, because as you know, this is not the easiest topic in the world that can happen. Okay, so what is Hamiltonian formulation?
Can I say?
Yeah, go ahead. That's why I'm
Okay.
asking.
So there's a theorem with a proof made by mathematical induction that every operator can be equals the integration of some creation operators, some matrix, some table, and the annihilation operators, and it's integrated by every state. So the spin type of particle and momentum. So
Okay.
for example,
Mhm.
Hamiltonian equals integration the Q, because Q equals all this important information about the particle, so the spin, momentum, and the type of the particle, and annihilation operator, annihilation operator, annihilation operator, and up to the number of the particles. The same with the creation operators and some constant that gives us information about the the purpose of this operator. I think that it's quite complicated to say it in English.
All right, but maybe I will refer to a simpler thing. So Hamiltonian, do you remember the concept of so-called the concept of Schrödinger functional? What is Schrödinger functional? Maybe fact. Okay, so this was fourth fact. Fifth fact. What is fifth fact? Wojtek, do you remember what is Schrödinger functional?
Functional.
Yeah.
No, I don't think I ever met the Schrödinger functional yet.
I'm sure you did, but you don't realize that you did. The fact. Reference of Hamiltonian in the second quantization to Schrödinger functional. And so this was like average value of energy across the whole space is what? If you want to compute, I will ask you if
This. So it's bra state. The Asian value of Hamiltonian operator and the cat vector.
Yes, so you are saying to me that this is like that, and what was bra, right?
Bra, yeah, because it comes from Dirac. No, meaning
Yeah.
because bra and cat, we have bracket because
Okay.
this type.
Functional from reference of Hamiltonian second to Schrödinger functional for in first quantization. Okay. So, and can you give me explicit? Maybe Arthur can give me explicit.
You mean
Arthur.
the integral of that?
Yeah.
Yes,
Yeah.
so it's integral of psi
Limits,
star
integral limits, please, first.
minus infinity to infinity
Mhm.
of psi with the star. Yeah, times h. Or just the energy.
Okay, just position
energy.
first.
Yeah,
Okay,
yeah,
and
the function of x.
I want
Then
a full
you can
structure of
you can write
Hamiltonian.
you can write
Give me
Hamiltonian times
Okay, give me right now the full structure of Hamiltonian. So what I need to write right now?
Minus h bar square
Mm-hmm.
2m
Mm-hmm.
times the Laplacian.
Okay,
Yes,
let us do
or
in one
just
dimension.
one dimension
Okay.
plus v of x. And the
Mhm.
whole thing times psi of x dx. Yeah. And
Yeah, so
you can write it as the Hamiltonian times ket of psi. You can write
yeah,
as e
it's already
times psi from the Schrödinger equation.
a
So
times. Oh, I see.
e
Yeah. So we can write it in that
it's
way.
very
Yeah.
simple because e you can take out from the
Right.
from the
You are absolutely.
integral because the is constant, and then you have psi module of the psi square in the integral, so it's just 1. So
Okay, dx.
the whole thing equals e.
Okay, so this is E is
Constant.
always position independent, right?
Yeah.
Okay, so this means I can take it and this integral is equal to 1, of
because
course.
it's of course integral from the
Yes,
probability density.
right. So we have such values since normalization holds. Okay, so this is okay, so this was for a single particle, but actually what we used to say this is a functional because this is a functional. So in a sense, you can make probing functions here, right? You understand what I'm saying? Probing functions, right? Right? Mm. So, but you can make a guess, random guess of psi. And for any function that deviates from it, this so true solution is always minimum. Okay, so for any random function C1 equals Cx plus dx, we have that Hamiltonian of C1. So if you, instead of psi, if you place slightly misshaped psi, you are close to solution, but you never achieved solution. So you have always, the fact is that its functional is bigger or the same. So in a sense, true solution always minimizes Schrödinger functional. Do you understand what I'm saying? Wojtek.
Yeah, I think so. I have a little confusion with this functional, but yeah, right now I think that's clear.
Because you
And
can
you have
see,
to move
you can be semi-intelligent monkey and you can make a guesses. You know what I mean? If so everybody is, we are a little bit part of monkey since we are just 2 million years after some evolution, right? So in a sense, we have some monkey part. So in a sense, we make a guesses. So true solution always minimizes Schrödinger functional. Okay. And approximate solution nearly true. Nearly true. Nearly true. Takes higher Schrödinger functional values. So we can justify. You understand what I said, right? Wojtek, do you understand what I said?
I don't know what you are
So I'm
thinking
saying
about
if I give you some exotic
approximate solution.
Wojtek, I give you very exotic potential in one dimension, and I will ask you to make a guess. Analytic function guess, right?
Okay.
So you can make a guesses, and you will see how close you are to the solution by observing the convergence to some minimal value, right? You understand? You will get some values for different.
The only question is why we are talking about these approximate solutions that take higher Schrödinger functional values.
Okay, because one-dimensional is trivial, but 2 and 3-dimensional, one particle in one dimension is trivial. But interacting particles in 2 and 3 dimension, 2 and more interacting particles are very difficult to solve.
But the true solution always minimizes the Schrödinger function. So
Wojtek, if I give you
solutions must have
if I give you
higher Schrödinger function values.
Wojtek, if I give you 10 interacting particles, believe me, it will be not that easy for you anymore. Or just 5 interacting particles. So you will, this is, in quantum chemistry, they don't care about toy models from mathematical physicists. They want to know real solution. So they need to make a shooting guessing methods. So this is very important theorem that always holds.
Okay, but
this is valid.
This approximation part of it is contained in this first part.
Yeah,
the
but this is
minimizes Schrödinger.
But Wojtek, it can be proven. What I said, it can be easily proven that. So in a sense, this is functional. formulation of Schrödinger equation. So in a sense, true solution of Schrödinger equation always minimizes Schrödinger functional. That's it. You
Okay,
can prove it from so it's just different way of
that's
looking.
not the problem. My question is why we are
Yeah, go ahead.
thinking about approximate solutions, maybe not thinking. From the first sentence, the second part must be always true because of the first one. So I don't
Yeah, but
find
Wojtek,
why we are
because
highlighting it.
in very real way, in most n particle interacting problems, you need to make very intelligent guess. Very intelligent guess about structure of wave function solution. And then you will always see how good is this guess by subsequent of trials where you observe Schrödinger function or how it does minimize. Because you never know what is the solution. You know, for n particles, you never know what is the solution. It's not like so this is very useful tool. And why I'm saying that? Because this fifth fact will refer to the general formulation of quantum mechanics. Yeah, so you have to go from, yeah, so how you write down the Hamiltonian then? The Hamiltonian in second quantization. How do you write it down? Okay, so now observe sixth fact. Sixth fact is going from Hamiltonian in first quantization into second quantization is done by scheme. Okay, now I will write this directly from a book, but I gave you the taste why it's like that. So this is spin, by the way. Right? You understand?
Okay, you have to move the camera.
By the way, we need a book, Białowieski-Birula, on quantum mechanics. This guy is very good. Okay,
Yeah,
so what
great.
we have,
Great man.
yeah, I think he's still alive. And his
Yes,
father,
yes.
I met him. Actually, one time I gave a seminar at Centrum Fizyki Teoretycznej Polish Academy of Science, CFT. It's even recorded. Maybe I should shift to my YouTube channel.
What's his
But
name? One more time.
Białowieski-Birula. Actually, there is Birula family. Look, people think there is Birula family that they're also famous in mathematics, and but there is Korodecki family that is famous in physics. So you see in Gdańsk. So there are families, there are like clans of scientists. So not everywhere there's so many professors like in Białowieski. In Birula, I don't know, Białowieski or Birula, this is family, probably. Yeah, anyway, I know there's another mathematician, kind of Białowieski-Birula-like. So anyway, just look. So we take Hamiltonian from first quantization. Wojtek, do you see? Hamiltonian from first quantization. And we have, so we are writing, so now you see, we are writing like Schrödinger functional. Do you understand? That second quantization Hamiltonian, this is like second quantization Hamiltonian. Right? You understand?
Yeah.
Yeah, so we have it like this. So plus many particle case. And double integral, of course, because we didn't do two particle case, but I am just writing you down, right? Wait, do you understand? You understand, right?
Yeah, I think so.
So we have a creation of one particle, R1, and then at that story is not yet over. So then I will VR1, R2. Yeah, and of course we have also H2. It's not written here, but it's of course this is also copied. And then we need two fields. Okay, sorry, this was both. So annihilation is on the left, and then okay, dr1, dr2. So do you understand now, Wojtek, that in a way the Hamiltonian in second quantization is like functional Schrödinger functional with creation and annihilation operators for fields, right?
Okay, I understand it.
Arthur, do you understand it? Arthur,
Yes, I understand it.
do you understand it?
I think so. Yeah.
Okay, we are almost done, but not yet. So, okay, and then, so it's very historic fact because two high school students, well, students, not only high school students, but in a way also and one undergraduate student is doing second quantization, which is usually done on graduate level. So this very, very unusual fact, by the way. Okay, and we are so, and now this is sixth fact, and then we have second quantization. Oh, yeah. Seventh fact. Okay. And what is the seventh fact? The algebra between psi, what is the algebra between psi and between field operators? What is algebra? Commutator of field operators.
So it is I times
Yeah.
the derivative.
Okay, if I can,
I'm not
yeah, okay.
sure.
Let's start algebra for is given as, okay, so can we write a commutator? So first, if commutator is set to 0, what does it mean? If that, in a sense, doesn't matter whether first particle is, yeah, so how would you behave? How would you behave? Okay, so if, by the way, so is given in different way for bosons and fermions. So if I create two particles and exchange them, what is the algebra of it? So we have commutator. Okay, just formality. AB.
Okay. If it will be
Is a,
for bosons, if it will be 0, it'll be
1 second.
Okay. It'll be
And
on the commutator.
I'm just,
No.
because
No.
not only you, guys, I'm
Oh,
also warming
sorry.
up. I am also on daily basis, I'm surrounded by experimentalists. So they don't like me too much anymore because I like too much equations, you know. And so this is anti-commutator, right? So if I can, so what does it mean? If two particles can be, if commutator is 0, it doesn't suggests symmetric wave function, right? Wave function, right? And this one, if it's 0, okay, so let's say if this one is 0, suggests symmetric wave function. Do you agree?
Yes.
Okay. And this one is 0, suggests antisymmetric wave function, right?
Yes.
And this is as in fermions, right? Right? Right or not? Do you agree?
Yes. Right.
Okay, so that's a first thing. So and yeah, I forget to mention very important thing before. In our prototype, what is the commutation relation between creation and annihilation operators in case of harmonic oscillator? Wojtek, please let me know.
Once again?
In a harmonic oscillator, there is commutation relation between, what is the commutation relation in between creation and annihilation operators in case of harmonic oscillator in first quantization?
So between this A's, the A and
Yes.
A dagger?
So I'm asking you, what is this value?
It's
A dagger
one.
A.
No, it's one.
Yeah, it's very important. So because we'll use this algebra later for operation. Okay. Okay, let me move on. And now, so for fermions, we have what for fermions? How much it is equal for fermions?
So, there's conjecture of the R vector there, or is the time derivative? Does
No,
this
no, no.
prime
This
means
is different position. So this is like position A and this is position B.
So
So you can write
IH bar Dirac's delta thing. It must be Dirac's delta. I know that.
but this is like so what is this? This is position of R, position of R prime plus R prime yeah, so how would you interpret it? So this is because this is anti-commutator. So what does it mean? Okay. Yeah, but maybe before answering this question, if I have analogy with harmonic oscillator, if I have it, so here there is DAGA, there is no DAGA. So here is annihilation operators and creator operators, right? Understand? It is equal to what?
It is equal to the for first it'll be this psi times psi conjugate plus conjugate psi times
Yeah,
psi.
of course, by definition, right. But to what it will be equal to? What's the postulate? Is this somehow similar to harmonic oscillator commutator here? Please understand that harmonic oscillator is boson because this is like excitation energy. So we can postulate Dirac delta actually. I want to say this one. It's a postulate of this theory, and so this is the first thing, and okay, because it has included. But Wojtek, if I have what is value AA commutator, what is the value?
so? Whether once again you have to move.
What is the value of this? Value of this AA. Huh?
Wait a sec. If
This
it should
is
be
one.
it should be
Yeah,
0.
of course. So this suggests that the value of this guy is what?
Is it's 0.
So we have such situation that R prime is 0. For fermions. But for bosons, how would be for bosons? What would change if we shift from fermions to bosons? So it is like shift from anti-commutator to commutator, right? You understand what I'm saying?
Yes.
Right. So basically it means that we have pretty much the same relations. Sorry, this is commutator. Or bosons. So we have predefined the algebra of operators, right? So yeah. Is it useful information for you, Arthur? Is it useful? What I had said today.
Arthur is out of the meeting. He wrote to me that he apologized, but he have to go right now.
Yeah, sure, of course. All right. So anyway, was it sufficient introduction to second quantization, or you want to have more? Because
Yeah, it
probably
was quite. But what you are thinking about a little bit more. If you are thinking about doing it today, I'm not sure I have the time for it. But
yeah. I
in
also
the
don't
next,
have
if you are thinking about next lecture, I think it will be quite interesting.
but I think it was quite warm. Today was warming up. So I have
Yeah, I
not
can
yet,
agree.
I have not managed to touch the Barone book yet, but it was just warming up. And remember, electrons are fermions, right? So
Yeah.
we will deal with it. All right, so it's a couple of pages, but for you to master, it's the best if you can write down on your own board. Or so there are 7 facts that are necessary to understand it initially, and then you in practical way, to be very honest with you, there's very rare cases where second quantization is really useful. It's because you have to assume coexistence of many particles and possible interaction between them. So it's quite challenging to solve, to tackle with, right? So it's a powerful tool, but just for limited number of cases. And it's quite nightmare to testify things numerically because you have to integrate many integrals to compute. Anyway, this is Taste of Fetter-Walecka book. So we are entering a kind of graduate level in knowledge of physics, basically right now. So that's what I wanted to say. Maybe the last thing which might be useful is just any operator, like from first quantization, operator from first quantization into second quantization. So it's 9 fact. 9 fact is simply by This is second quantization. So you have to everywhere use this, unfortunately, you know, this integrals and creator and annihilation operators. So this is very, very time consuming. But it turns out that in most problems, you always get first insight with the first quantization. So second quantization is usually a, so this is first quantization. You understand, Wojtek, what I'm saying?
I think.
And also, yeah, so and then it's A and B particles, creation and operators. So we'll deal with it.
Okay,
And
but
also,
I apologize, but as Arthur, I need to go right now.
yeah. Anyway, it's good, guys, that we met. So,
Yeah.
all right. So, Wojtek, please stop recording right now
Okay.
and send me this recording. This is very important recording. Okay, please stop it.